Hello everyone, I hope you are doing well. In this video, we are going to solve problem 28 from chapter 1 of solid state physics by Wahab. The chapter name is atoms in crystals. The solutions to other problems are already uploaded. They include solutions from problem number 17 to problem number 27, and I have uploaded solutions to all of these problems, and some of them were left, like problem number 28, 29, 30, and some of these initial problems. So I decided to upload them all and one by one, so that you may not find it difficult to. And I will upload from other chapters as well, from different books as well, because I know some of the students are following solid state physics by Wahab, others are following Kittle, solid state physics by Kittle. Others are following material science and engineering by Callister. So there are tons of problems. I have listed all of the books whose solutions I have uploaded from time to time, and I'll keep on uploading them as I get time. So let's quickly get started with problem number 28, because it's the problem that we are solving today. It's like a problem statement says, here it is, interatomic spacing, interatomic. Now please focus on the words being used. Sometimes it's interplanar spacing, it's a different thing. Interatomic spacing is a different thing. Okay, you have to deal it differently. So yeah, it's interatomic spacing of silicon which has diamond lattice. It has some spelling problem, but we have understood that it has a diamond lattice structure, silicon. It's 2.35 angstrom. So that the data which is given is like interatomic spacing is given, which is 2.35 angstrom, and we have been told that the structure of silicon is diamond. And calculate the density, we need to calculate the density of that structure, and we are given with the atomic weight of silicon is 28. So this information is given, and we need to find out the density. The final answer is given for convenience to confirm, whether the answer we have calculated is correct or not. So yeah, let's get started. We have seen the statement, and now we know the data we have. Let's first write the data we are given. Interatomic spacing, which is let's call it as I. I'm just calling it as I. You can use any other notation that you are comfortable with. Okay, this is the interatomic spacing. And interatomic spacing, nearest neighbor distance, in other words. Okay, because we are more familiar with nearest neighbor distance than interatomic spacing. Okay, so interatomic spacing is actually the nearest neighbor distance. Nearest neighbor distance. Okay, is equals to I as well. Alright, and we need to calculate density. This is rho, which shows density. Atomic weight is given, which is capital M. I'm just representing it with capital M, which is molar mass. Molar mass is another word for atomic weight, and it's 28. Its units are gram per mole. Okay, and since we always put things in SI units, okay, all the quantities that we are inserting in formula, they all should be in SI units, and for that purpose we have to first convert this into kg before inserting it into the original equation for the calculation. So for our convenience, let me first convert it. 10, we are multiplying 10 raised power minus 3 as well as 10 raised power plus 3, so that the situation remains neutral and mathematically consistent, and 10 raised power minus 3 remains as it is. We know K, which is kilo, is actually 10 to the power 3. We can write in place of 10 to the power 3 as kilo, G as it is by mole. So also we have converted the molar mass into SI unit. Okay, so this is done. And molar mass is different from the mass of the sample or or element. Molar mass is a different thing. That is why you can see that its unit are not kg but kg per mole. And yeah, now let's move towards the solution. We know that the density is given by density is given by this formula, total mass of unit cell of atoms in a unit cell, obviously, divided by the volume of unit cell. Okay, since diamond has cubic FCC structure, that is why its volume will be a cube, where a is the lattice parameter, not interatomic spacing or atomic radius. Okay, you have to be specific with the words being used. So it's a cube, which shows the interatomic spacing, and the total mass of unit cell is equals to the mass of each silicon atom multiplied by the total number of atoms per unit cell. Okay, so the total mass of unit cell will be actually, for example, we have lattice, maybe roughly I'm saying, maybe they are 10 atoms in a unit cell. So the total mass of the unit cell will be equals to simply the total number of atoms that we have multiply the mass of each atom. It's just like if we have 10 toffees, if we similar toffees, and we know the mass of each toffee, then we can simply find out the total mass by multiplying the total number of toffees we have, which is 10 to the mass of each toffee. That's a simple thing. Okay, that's how I have wrote this, that the total number of atoms we have in a single unit cell of diamond shaped lattice multiplied by the mass of the atoms making up the lattice, which is actually silicon atoms. So we'll be using the mass of silicon atom. Before doing that, we should know the mass of silicon atom. We know the molar mass, but we don't know the mass. So this is a simple formula to find out the mass if we know the molar mass of single atom. Okay, this is the mass of single atom, not anything else. Is the mass of single atom. And to find out the mass of single atom, what you do is to divide the molar mass by Avogadro's number, atomic mass by Avogadro's number. This is always true if you want to find out the mass of single carbon atom, for example. If you know its atomic weight, you will divide it by Avogadro's number and you will get the mass of each single carbon atom. Okay, this is for one atom, not 2, 3 or 4, but one atom. So, and if you multiply with the number of atoms you have, you can find out the total mass of the sample you have. So we are interested in finding out the mass of single atom because the total number of atoms is adjusted by the capital N letter here. So that's an extra discussion, but you should know about it because this is the formula that you will be frequently using onwards. So you should understand what it gives you, okay, so that you may use it afterwards. So it's molar mass divided by Avogadro's number. We'll simply write it here. Molar mass over Avogadro's number multiply N over A cube. Now what is we know capital M, which is 28 multiplied by 10 to the power minus 3. Okay, Avogadro's number, which is 6.023 multiplied 10 to the power 23. But what is capital N and A cube here? We should know about it. And A is different from nearest neighbor distance or interatomic spacing. Okay, keep that in mind. So we first have to know about it. In diamond structure, net number of atoms per unit cell are 8. Okay, there is no time to justify it. Okay, in diamond we have actually 8 atoms at each of the corner of the cube. Okay, and their 1/8 part is contributing to the unit cell, so that we have 8 atoms. So 8 into 8, 1/8 into 8 gives you 1. So corner atoms contribute as a whole 1 to the whole unit cell. Now besides that, since it is FCC, so there are additional atoms at each of the phase of the unit cell, which are total of 3, which contributes a total of 3. And besides that, we have 4 atoms at the tetrahedral position inside the diamond lattice. That is what makes it different from the normal FCC cube. Okay, there are additional 4 atoms in the inside the unit cell. So besides these cubic type of atoms, we have 4 additional atoms, which makes total of 8. Okay, this is related to understanding the crystal structure of a diamond. So you should remember it. Okay, the simple thing is to remember the net number of atom in a diamond lattice, which will always be 8. Okay, if it is a diamond lattice, okay, if the structure is diamond like, then the net number of atom will be 8 for sure. And here for silicon as well, we'll use 8 here. And for A, we should know the relationship between nearest neighbor distance, which we already know, and the lattice parameter, which is A here. A is the lattice parameter, which is the length, these side lengths from one corner to the other corner of the unit cell along the axis direction. These are the lengths A. And what we are given is the interatomic spacing or nearest neighbor distance, which means the distance of a silicon atom from its nearest neighbor is what interatomic spacing is. And it is given by nearest. We besides that, let's say it's equation number 2. We know that, we'll pretend that we know that, and you should remember it as well for diamond structure, because there are some structures like cube, BCC, SC, FCC, whose some of the parameters you should remember on your fingertips when you are actually studying them in detail, because we don't want to spend our time or waste our time in deriving the same relation again and again if you are using those relations frequently. Okay, so it's easy to remember those formulas, and we can obviously understand how to derive them and how they are, the way they are, so we can justify them. We should know how to justify them, but it's not always necessary to derive them again and again. We know that the nearest neighbor distance, the nearest, okay, neighbor distance is given by in diamond. Okay, it is true for diamond structures. I called it I, the nearest neighbor distance, and it is equals to under root 3 by 4 into A. Okay, where A is the lattice parameter we are interested in. So if you want to find out A, it will be simply, it's not 9, okay, it's A. It's cute little A. No, it's not Q, it's A. Let me take 4 here, so it's 4I by under root 3, so that A is left alone here, and we wanted to calculate A. Let us now put the value of I here, which we already know, which is 2.35 angstrom. Angstrom is 10 to the power minus 10 meter. Okay, we don't need to mention the unit meter here. I don't know if you noticed it or not, but you can see that angstrom is a prefix that consumes the unit as well. Okay, angstrom is equals to 10 to the power minus 10 meter. Okay, it includes the unit as well, while other prefixes like mega, tera, they always are outside the unit. They don't consume the unit. Okay, they don't include the unit, but angstrom includes it. So if you see this, you don't need to mention meter with it, because meter is consumed in angstrom itself. So let us calculate this and find out A. Okay, let me use the calculator. You can see here it's 5.427 multiplied 10 to the power minus 10. So this is what we are gonna use, okay, meter in formula number 1. Okay, now we know all the things here in this formula, and we just need to put those values right into the formula to get the result we are seeking. Okay, so let me put all of these values right into this equation number 1 or formula number 1. So let's put these values. Molar mass is 28 multiplied 10 to the power minus 3. Keep in mind SI units. Okay, so capital N is just a number which is 8 divided by Avogadro's number which are 6.023 multiplied by 10 to the power 23. Okay, and a cube, a was calculated to be this. Okay, let me put it right here. It's 5.427 multiply 10 to the power minus 10 with whole cube on it. Okay, let me calculate it using the calculator. And so you can see here it's 2326, the result that we wanted. Okay, 2326, you can see here this is the result, and we are done with this problem now. Okay, kg per meter cube, this is row and answer. I hope you got it, and if you have any questions you can ask me in comment section. And is another good news for you people. I have organized all of the problem solution separately for different books. Basically what I did now is that I have organized the problems and solutions based on the book I am following. So I realized actually that there are 6 different books related to solid state physics that I followed based on your requests, based on my opinion that that's important. And for your convenience I thought to make grouping of them in different playlists. So there is a playlist named as Solid State Physics by M.A. Wahab Solutions, where you'll find problems and solutions related to that book particularly. Then there is another playlist, Solid State Physics by Kittle Solutions, where you'll find out the solutions of the problems from that book particularly. And similarly from different books, as I named all of them previously, you can see their names. So there are different playlists where only problems and solutions are added. If you are interested in concepts and derivations, you will find them in Solid State Physics 1 and Solid State Physics 2 playlist. So that is what I have did. I hope you understood what I did. Okay, if you have any question you can ask me. I'll link all of those playlist in the comment section. I'll pin it so that you can go to your favorite book problems, solutions and all. From my side I'm just trying my best to make it easy for you people to learn. Additionally, if you have any questions, if your concerned problem is not yet uploaded, you can simply comment and I'll upload it first before others. If you have any request as well, you can ask me in comment section. Good luck, goodbye, thank you. And one more request, please share this channel to other people so that I may get exposure it needs. Okay, so yeah, thank you.